Now we will be going to discuss the equivalent circuit of a transformer. You will see later that a equivalent circuit will be useful for calculating the performance of a transformer, the performance characteristics like voltage regulation, efficiency, etc. can be calculated from the equivalent circuit. Now, do you know what is an equivalent circuit? Now, I will take a simple example. For example, you have V is equal to IR. This is an equation. What is this equivalent circuit? In this equation, do you see an circuit? I will show that you have a voltage V and a current I and a resistance R. Can we not represent this with the help of a circuit? V is applied across a resistance R through which a current I flows.
Yes.
So this is the equivalent circuit of this V is equal to IR. Now I draw, say I write a circuit, say resistance and a reactance. This is the circuit I draw, and a voltage, say V is here, R and L, this is R. Now what will be the equation? V, I, R and L. Can you not write is equal to V is equal to I into plus J XL. So this equation is there. So this is the equivalent circuit of this equation.
Yes, ma'am.
Or this equivalent circuit represents this equation. They are equivalent, isn't it?
Yes.
Yes.
Now, suppose a phasor diagram is given, right? Say V is here and a current I is shown, I. This angle is phi. Can you draw the equivalent circuit? Do you see an equivalent circuit of this phasor diagram? You see voltage V is there, a current I is lagging the voltage by an angle phi. So the circuit should be an RL circuit.
Yes.
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 Do you get it?
Yes.
So a voltage V is here and current is I is flowing through a resistance R and an inductance L. So since it is an RL circuit, the X or L you write, since it is an RL circuit, the current will lag the voltage by certain angle.
Yes.
So these are equivalent, isn't it?
Yes.
So you can write the equation also, V is equal to I plus R plus
JXL.
XL. So all are equivalent. So if the phasor diagram is given, you know the circuit which represents the phasor diagram, or if the equation is given, also you can draw the phasor diagram and also the circuit. So from the phasor diagram which you have drawn, no load under load condition, you should be able to draw the equivalent electrical circuit,
Yes.
isn't it?
Yes. Yes.
So in this lecture I am going to discuss with you how to draw the equivalent electric circuit of a transformer from its phasor diagram. Is this clear to you?
Yes.
Now to test your knowledge now, I am drawing a phasor diagram. Say V is here and current I is here. This current is leading the voltage by an angle. Do you see an equivalent circuit here?
Yes.
What is the equivalent circuit of this phasor diagram?
Inductance.
Capacitor.
It should be a capacitive one. Very good. This voltage V is here and only capacitance or resistance and capacitance, because
Resistance
this
and capacitance.
leading. So
RC circuit.
say RC circuit, it could be RC or RLC depending on that C should be bigger, XC should be bigger than XL. So it could be RC circuit or an RLC circuit. So for each phasor diagram, there is an equivalent electric circuit. Is this point clear?
Yes.
Now let us refer to the phasor diagram of the transformer which you have drawn. Now from the phasor diagram, we try to draw the equivalent circuit. So on the primary side of the transformer, you had applied a voltage V1. Right?
Yes.
Now on the primary you have R1 and X1, the voltage drop R1 and X1.
Yes.
That should be represented by a resistance R1 and a leakage reactance X1, through which a current I1 flows.
Yes.
So what is the induced EMF here? E1. V1 minus E1 is equal to I1 R1 plus J of I1 X1. Is it clear?
Yes, sir.
Primary side we have drawn. So this E1 is induced in the winding. We can show an winding here. E1 is induced. Now this winding has no loss. That means, or no voltage drop. That means its resistance and reactance we have already represented here.
Yes.
So this is only a winding which does not have any resistance or reactance. We have represented them separately. Is it all right?
Yes.
It has resistance and reactance, but since we have shown them separately, so this is an ideal winding
Yes. Yes.
without having resistance and reactance. On the secondary side, EMF induced is E2. We can show this E2.
Yes. Yes.
And this resistance and reactance of the secondary we take out. So we show resistance R2 and reactance X2, through which a current I2 flows, and E2 minus I2R2 minus JI2X2 is equal to
V2.
So I show V2 here, which is across the load. I2 flows. This is your load, LOAD. Is it clear?
Yes, sir.
Now the primary I1, primary current I1 has two components, I1 dash and I0.
Yes.
Now in this winding I2 is flowing. So in this winding I1 dash is flowing. This is N1, this is N2. What is the relationship? I1 dash N1 is equal to
I2 and
I2 into
And
N2. So this is I1 dash. I1 dash is smaller than I1 by an quantity which is called I0. So some I0 I can show here. You see I1 is equal to, on this point you apply
yes. Yes.
this I1 is equal to ingoing current is equal to outgoing current. So I1 is equal to I0 plus I1 dash.
Yes.
Is it clear?
Yes.
I1 is incoming is equal to outgoing is I0 plus I1 dash. This satisfies. Now this I0 has two components. I0 has two components, IC and IM. IM is a current which lags the voltage by 90 degree. That means it flows through an inductance,
Yes.
because in an inductance current lags the voltage by
90 degrees.
So I can show an inductance here. I0 has two components of current, that is, this is IM. IM will be shown flowing through an inductance,
Yes.
and IC is the current which flows through a resistance because it represents loss.
Yes.
Say RC. or RM. So these two together you can connect here. So you see I0 has two components, IC plus IM. Here you apply incoming current I0 is equal to outgoing two currents IM and plus IC.
Yes.
And IM is the magnetizing current. IM lags the voltage by 90 degrees. So it should be shown flowing through an inductor. And IC is the loss component current. So it should be shown flowing through a resistor. So we have shown RM and XM. These two together is connected here. So this is the complete equivalent circuit of the transformer, which for which you had drawn the earlier drawn the complete phasor diagram. Now, but this is a coupled circuit. We can simplify this circuit and bring it to only a single circuit by making some approximations. How? You see this parallel branch I0 as compared to this I1 and dash or I1, this current, no load current of a transformer is very small. I0 is about 3% to 5% of the full load current. That means if you make an approximation of 3 to 5%, you can neglect this branch. Is it all right? So if you remove this parallel circuit, you make an approximation, and this becomes your approximate. This is the approximate
equivalent circuit.
Equivalent circuit of the transformer. You have made some little approximation by removing the parallel branch, but now this circuit becomes very simple. Now still it is two circuits. Now this circuit can be made into a single circuit provided these quantities of the secondary side is transferred to the primary side, or the quantities of the primary side is transferred to the secondary side. This is possible provided these two voltage level is same. Suppose this is also 400 volt, this is also 400 volt, and if the polarities are same, we can straight away connect these two. This terminal can be connected to this terminal can be connected to this. Because these two windings only represent a voltage only. This is a voltage. This winding has no meaning now. This is a voltage, you see. Because winding resistance and reactance have been taken away separately, shown separately. Now here you have a voltage level E2. Here what is the voltage level? This is E1, this is E2. Now these two terminals can be connected. These two terminals can be connected provided the voltage level is same. So what we do, we refer this quantity, convert these quantities to this voltage level, or convert these quantities to this voltage level and make a single circuit. Now for a convention, what we will do, if I transfer this quantity, say R2, X2, etc., to the primary side, we will call them R2 transfer to primary side, we will call, say, R2 dash. X2 transfer to primary side, we will call X2 dash. Similarly, if these quantities are transferred to the secondary side, R1 transferred to secondary side will represent by double dash. Reactances
X1 double dash.
X1 double dash, and so on. In that case, you can have a single circuit. Assuming that these are voltage levels are same, we can make connections. Otherwise, we just quantities, we say this quantity is transferred to primary side. So this will be represented by dash, this will be represented by a dash. And that's all. Now you see this becomes a single circuit. series circuit. Now these two resistances can be added.
Yes.
These two reactances could be added.
Yes.
Now what it becomes? You have a V1 voltage, you have one resistance and one reactance, and the load is connected. So what will be the simplified circuit? I rub it up and redraw this. Now here you see this approximate equivalent circuit. Now we will see how this resistance and reactances of the secondary could be transferred to the primary side, or the resistance and reactance of the primary side could be transferred to the secondary side, and what are their values. Now let us see what is the I square R loss in this circuit. Current is I1, so I1 square into R1 is the power loss. Now if this resistance is transferred to the secondary side, its value will be R1 double dash say. Then what will be the power loss? Current in the secondary side is I2, so it will be I2 square into R1 double dash. Now there will be no change in the circuit conditions if I1 square R1 becomes equal to I2 square into R1 double dash. From this equation we get the value of R1 referred to the secondary side as equal to R1 into I1 by I2 whole square. And as you know, I1 into N1 is equal to I2 into N2. I1 by I2 is equal to N2 by N1. So by substituting you get R1 into N2 by N1 whole square. Thus R1 double dash is equal to R1 into N2 by N1 whole square. To remember this, suppose what you have done here, R1 you have transferred to R2. So R1 double dash is equal to its own value R1 multiplied by, you have transferred to secondary side. So secondary number of turns divided by the circuit from where you have transferred, that is N1, N2 by N1 whole square. Now can you tell me what will the value of R2 when it is transferred to primary side? Let us see. R2 referred to primary side will be R2 single dash is equal to its own value R2. You have referred to the primary side whose number of turns is N1, and you have referred from the secondary side whose number of turns is N2. So N1 by N2 whole square. So this is how the circuit resistances could be transferred from one circuit to the other. Now similarly the reactances X1 from primary side could be transferred to the secondary side whose value will be X1 double dash, and X2 from the secondary side could be transferred to the primary side where it will be X2 single dash, and their values will also accordingly change because X reactance is proportional to number of turns square. Reactance is proportional to the number of turns square. Turns is the number of turns of the winding. So X1 referred to secondary side is equal to X1 its own value. You have transferred to secondary side, number of turns is N2, and from the primary side number of turns of primary side is N1, so square of that. Similarly say X2 you transfer from secondary side to primary side, so its own value X2 multiplied by primary side number of turns N1 and secondary side number of turns N2 square. So this is how we are transferring the values of reactances from one side to the other. So you have the supply voltage V1 here, and you have one resistance only, which you are called equivalent resistance of the transformer, that is R1 plus R2 dash, and one reactance Xc is equal to X1 plus X2 dash, and current I1 is flowing, and here you have the load, and this voltage is V2. So this is a simple series circuit representing the transformer, and it will be very easy now for you to calculate the performance of the transformer using the simple series circuit. Now you could have drawn the same circuit, equivalent circuit, referring all the quantities, primary quantities, to the secondary side. Can you draw it? Please try to draw the approximate equivalent circuit of the transformer, referring the primary quantities to the secondary side. Please draw it. See, on the secondary side you have voltage, how much? Induced EMF is E2 on the secondary side.
Yes.
And across the load you have V2. This is your load, and the current flowing is I2, and here you have the equivalent resistance and the equivalent reactance. This is RE. So secondary circuit resistance was R2, plus you have transferred R1 to the secondary side, and reactance is Xe, X2 plus
X1 double dash.
X1 double dash. So this is the approximate equivalent circuit of the transformer, having all the quantities referred to the secondary side.
Yes.
Is it not very simple now? Looks very simple circuit.
Yes.
And you can make any calculations of, like regulation, you can calculate what will be the voltage drop in the transformer resistance and reactance when it is loaded, so that you can calculate the percentage voltage drop. That is called regulation of a transformer.
Yes.
Have you got any question? The exact equivalent circuit of the transformer has been shown once again, where V1 is the primary input voltage. E1 and E2 represent the EMFs induced in primary and secondary windings. You can see from the diagram, I1 dash is the additional current drawn by the primary winding to counterbalance the secondary MMF. That is, I2 into N2 is equal to I1 dash into N1. Now the sum of I1 dash and I0 is equal to the total current drawn by the primary winding, that is I1. Now R1 and X1 are the resistances and leakage reactances of the primary winding, and R2 and X2 are the resistances and reactances of the secondary windings. I0 is the no load current, and it has got two components, that is Im and Ic. Im produces the flux which is shown flowing through magnetizing reactance Xm, and Ic represents the loss component of the no load current which is shown flowing through a resistance Rm. Now let us see the approximate equivalent circuit where we will neglect the no load component of the primary current. Here we have shown you the approximate equivalent circuit of the transformer where we have removed the parallel branch, that is the branch where through I0 no load current was flowing. This we have done to simplify the equivalent circuit. In this process we have made an approximation to the tune of 3 to 5%. As you know, the no load current of a transformer is about 3 to 5%. Now in this diagram you see that I1 is now approximately equal to I1 dash, as I0 is taken as negligible. R1 X1 are the resistance and reactances of the primary winding, R2 and X2 are the resistance and reactance of the secondary winding. Now in the next diagram we will show how these two circuits could be made a simple single series circuit. In this circuit what we have done is that we have transferred the resistance and reactance of the primary circuit to the secondary side. That means R1 has now gone to the secondary side and has been added with R2. So that is called R equivalent, that is Re. Re now is equal to R2, the resistance of the secondary winding, plus R1 double dash, that is primary circuit resistance R1 referred to the secondary side. Similarly, reactances also have been added together to give to an equivalent reactance Xc on the secondary side, which is equal to X2, that is secondary circuit reactance, plus X1 double dash, that is primary circuit reactance X1 transferred to the secondary side. The value of R1 double dash is equal to R1 multiplied by N2 by N1 whole square, and the value of X1 double dash is equal to X1 multiplied by N2 by N1 whole square. Here you see the secondary quantities, that is R2 and X2 have been transferred to the primary side and added with the primary side resistance and reactance to give Re, which is equal to R1 plus R2 single dash, and Xe is equal to X1 plus X2 single dash, and their values R2 single dash is equal to R2 into N1 by N2 whole square, and X2 single dash is equal to X2 into N1 by N2 whole square. Now how these values have come, that is the referred values of resistance and reactances either on the secondary side or on the primary side, have already been explained to you earlier. You have understood this?
Yes. Yes.
Okay, then in the next lecture we will be discussing the calculation of voltage regulation of a transformer using the approximate equivalent circuit.